Good afternoon, students. In the last class, we studied about the fission reaction. In the nuclear fission reaction, heavy nucleus is bombarded with a slow-moving neutron. That nucleus is split up into the two light nucleus, and at the same time, there are two or three neutrons are liberated. At the same time, there is a large amount of energy is liberated in the nuclear fission reaction. That is a nearly 200 mega electron volt. In the same time, nuclear fission reaction is also called as a chain reaction. And the chain reactions, in the nuclear fission reaction, there are two types of a nuclear reaction. One is known as a controlled nuclear fission reactions are two types. One is a controlled chain reaction and the second one is known as an uncontrolled chain reaction. Controlled chain reaction is stopped when you want, and the uncontrolled chain reaction is that when it is a start, it does not stop. For the example, nuclear bomb. And the nuclear chain reaction or the controlled chain reaction is that when you want to stop that reaction is stopped. And the example for the controlled chain reaction is a nuclear reactor. So in the last class, we study about the nuclear reactor. So the nuclear reactor is a device which convert the nuclear energy in the other useful meaning. So in the last class, we study about how the nuclear reactor controls the neutrons because the nuclear fission reaction is a totally depends upon the neutrons. And in the nuclear fission reaction, the neutrons, those are liberated, those are very fast moving and those are energetic. But when the energy of those neutrons is absorbed, that time again those neutrons are participant into the nuclear fission reaction and that reaction is a chain reaction. So today we study about the nuclear fusion reaction. Nuclear fusion reaction. For the nuclear fission reaction, there is no condition for the temperature. That reaction is takes place at any temperature. If the slow-moving neutron is given to the heavy nucleus, that nucleus is split up into the two parts. But here, the nuclear fusion reaction, there is a condition is that to find out the nuclear fusion reaction, there is a large amount of temperature is required. So there is a large amount of temperature is required to fuse the two light nucleus. The nuclear fission reaction is possible for the heavy nucleus and the nuclear fusion reaction is possible for the light nucleus. Because when the two light nucleus are combined or two light nucleus are joined together to form a heavy nucleus or to form a one nucleus, that reaction is known as a nuclear fusion reaction. So here, nuclear fusion reaction is that nuclear fusion reaction is that in which two light nucleus are binds together to form a one nucleus and to find out a heavy nucleus. By liberating large amount of energy that is a Q. So here, this nuclear fusion reaction is a very difficult as compared to the nuclear fission reaction. Because for the nuclear fission reaction, if the slow-moving neutrons are bombarded to the heavy nucleus, that nucleus is split up into the two light nucleus. But here, the two light nucleus are binds together. To bind the two nucleus, it is a very difficult to split the heavy nucleus into the light nucleus. Because the two light nucleus are bind together, means there is a large repulsion force is find out in between the two nucleus. Because these two nucleus are positively charged and there is a repulsion is find out in between the same nucleus. When the two nucleus are binds, means there is a large repulsive force is find out. To remove that repulsive force, to remove the electrostatic force, those two nucleus are binds together. So to bind these two repulsive nucleus, there is a large amount of energy is required. So this reaction is possible at a very large temperature, and this nucleus or this nuclear fusion reaction is find out on the surface of the sun. Because sun radiate per second, there is a large amount of energy. So there is a large amount of energy is find out on the surface of the sun, and we know that the sun is made by the portion of a sun, or the 90% portion of a sun is made by the light nucleus, means such as hydrogen, deuterium, helium, carbon, nitrogen. In this type of, there are large number of a light nucleus are there. So this as well as the sun radiate the energy, and that energy is known as the thermo energy, and this thermo energy is possible due to this thermal nuclear fusion reaction. Because at per second, at that time, there are large number of fusion reactions are taking on. So when the large amount of fusion reactions are takes place on the sun, that time in each reaction there is a large amount of energy is liberated. When the large amount of energy is liberated, and there is a collection of a large amount of energy, because there are large number of a light nucleus are there, and already there is a temperature is there. At that temperature, there is a nuclear fusion reaction is a takes place. Means that is a hydrogen to deuterium, deuterium to helium, helium carbon. In this type, there are number of nucleus, or there are number of a chain reactions are takes place. So in this type of, this nuclear fusion reaction is a possible at a high temperature, and this nuclear fusion reaction is a possible on the sun, and because of this fusion reaction, the sun radiates a large amount of energy. So here for the example of this example, if two protons are combined to each other, when the two protons are combined, means that time we have got the another one nucleus, or when the two deuterium nucleus are combined, when the two deuterium nucleus are combined to each other, and it is a possible for at a high temperature, then we have got 2 plus 2, that is a 4, and 1 plus 1 2, means there is a nucleus which is a find out, and that nucleus is known as a helium. So when the two light nucleus are combined to each other, and this process is known as a nuclear fusion reaction. So in this nuclear fusion reaction, when the two deuterium nucleus are combined, we have got the new nucleus, and that nucleus is known as a helium nucleus. At the same time, there is a large amount of energy is liberated. So this large amount of energy which is liberated, that is a more than the 15 mega electron volt. So here these deuteriums are combined to each other. So it is a very difficult to combine the light nucleus to in the form of a helium, because this deuterium nucleus has a positive nucleus, as well as this nucleus is also positive nucleus. So combine both the nucleus and form a one nucleus. There is a large repulsive force is a find out. To remove this large repulsive force, there is a large amount of energy is required. There is a large amount of temperature is required, and the temperature is more than the electrostatic force of attraction, repulsion in between the two nucleus. So that time this process is a find out, and we have got the new nucleus, and that nucleus is known as a helium. At the same time, there is a energy is liberated. We know that the energy liberated in the nuclear reaction is depends upon the mass defect. So the mass of these two nucleus is more than the mass of this nucleus. Means there is a mass defect is find out, and that mass defect is converted in the form of energy according to the Einstein's mass energy relation. So here this mass defect is converted in the form of energy, and this energy which is liberated in the nuclear fusion reaction is less as compared to the energy which is liberated in the nuclear fission reaction. We know that in the nuclear fission reaction, the energy liberated is more than the 200 mega electron volt. But in this, the energy related is more than the 50 mega electron volt. But these reactions are possible at a large temperature. So here, the energy liberated in the nuclear fusion reaction is less as compared to the energy liberated in the nuclear fission reaction, because in the nuclear fission reaction, mass defect is more, and when the mass defect is more, that time the binding energy is also more, as well as the energy release is also more. So here, in this reaction, the mass defect is less, and therefore the binding energy is also less, and the energy which is liberated, that is also less. So in this type we study about the nuclear fusion reaction. So nuclear fusion reaction is that in which the two like nucleus are binds together to form a nucleus, and in this nucleus there is a energy is liberated, and to find out this type of nuclear fusion reaction there is a high temperature is required. So in this type we study about the chapter nucleus, as well as in this chapter the important numericals are there. Then we study about the important numericals in this chapter. Calculate the energy released calculate the energy released in mega electron volt by 1 gram of 1 gram of uranium 235 in the following fission reaction. In the following fission reaction, there is a reaction is given in the numerical. Uranium 235 is bombarded with a neutron, thermal neutron. It is split up into the two like nucleus, and those are barium plus krypton. Barium 141 and 56, and the krypton 92 and 36. The reaction is given in the numerical 3 neutron. So here this is a reaction which is given, and this reaction is in the form of a nuclear fission reaction. And in this nuclear fission reaction, when the neutron is bombarded with the uranium nucleus, it becomes as a heavy, and it is split up into the two like nucleus. At the same time, there are 3 neutrons are liberated. In this question, we want to find out the amount of energy which is released in this equation. So to find out the amount of energy which is released in this equation, there are some values are given. So here the values those are given. Mass of uranium is given. Mass of uranium 235 is given. That mass is a 235.0439 AMU. The atomic mass unit is measured in the form of the mass is measured in the form of atomic mass unit. The mass of Ba, that is a 141, is given, that is a 140.9178 AMU. The mass of krypton is given, that mass is given as a 91.8854 AMU. Mass of neutron is also given, that is a 1.0087 atomic mass unit. So here, in this question, all the values are given. So this question is carries 5 marks in the theory exam. So here the mass of uranium is given, mass of neutron is given, mass of barium, krypton is given. Then the question is, what is the amount of energy is released in a 1 gram? So first to find out the mass defect, then we find out the binding energy, and the binding energy is equal to delta M into 931, and delta M means nothing but a mass defect. So first to find out the mass defect, then we find out the binding energy. We know that the related formula for the binding energy is equal to delta M into 931. So here, first to find out the values, that is the RHS and the mass of a product, mass of a reactant, and the mass of a product. So first to write out the mass of uranium 235 plus mass of neutron. Write down the mass. All the values are given. 235.0439 AMU, and this mass of a neutron is given as a 1.0087 AMU. So here, at the same time, find out the mass of then write down the mass of a Ba141, mass of a krypton 92, as well as there are 3 neutrons are there, mass of it 3 neutrons. So write down the mass and add those values. First, mass of barium, that is a 91, 140.9178 AMU. Mass of a krypton is given in the question 8854, and mass of a 3 neutrons. So multiply the value of a neutron 1.0087 AMU. So add all these values. When we add all these values, we got the answer. So the mass of a product and mass of a reactant separately. So find out the mass of a product, that is a 235 236.0526 AMU before fission. So this mass is a before fission, and after fission this is the mass. So after fission, calculate, and this mass is a kind of 235.8293 AMU. So here, mass of the nucleus before fission is more than the mass of our nucleus after fission, because this mass is considered in the form of a mass defect, and that mass defect is converted in the form of a binding energy. So find out first the mass defect. So when we find out the mass defect, that is a delta M. Mass defect is equal to mass defect, that is known as a delta M. Delta M is equal to 236, means the mass before fission, 236.0526 minus this mass 235.8293. We have got the mass defect, and that mass defect is 0.2233 AMU. So this is a mass defect. But the question is that what is the energy which is released for the 1 gram of a carbon? Sorry, 1 gram of a new uranium in the one nuclear fission reaction. So in this type, we have got the binding mass defect. Then what is the energy release? So we find out the delta M in one nuclear fission reaction, that is a 0.2233. Then find out the binding energy. Binding energy means the energy released in the one fission reaction, that is a delta M into 931 mega electron volt. Therefore, 0.2233 into 931. So the answer is the mass which is released in the one fission reaction is 207.9 mega electron volt. So this is the energy released, or this is the amount of energy released in the one nuclear fission reaction. So this is the Q amount of energy which is released in the nuclear fission reaction. But the question is that this energy is released for the one atom, but here the amount of substance is given as a 1 gram. Then find out the number of atoms those are present in the 1 gram of uranium. Then find out the total energy which is released from the 1 gram of uranium substance. Then find out the number of atoms those are present. Number of atoms in number of atoms in 1 gram of a uranium. So to find out the number of atoms, use the Avogadro's number, that is a 6.023 into 10 to the power of 23. Here the amount of substance that given as a 1 gram divided by the atomic mass number, and the atomic mass number is given as a uranium-235. So calculate this value. We have got the number of atoms and the number of atoms into the energy release. So when we multiply that value to this value, so therefore Q is equal to 6.023 into 10 to the power of 23 into 1 gram of a uranium divided by 235 into the energy release in the one fission reaction is a 207. Then what is the amount of energy release for 1 gram of a uranium? That is a 207.9. So the answer is equal to, the answer is 5.33 into 10 to the power of 23 mega electron volt. So in this type we solve this question. Here all the values are given. So first to find out the mass before fission, then find out the mass after fission, subtract both the values, that mass before fission and mass after fission. Then we have got the mass defect, but the question is find out the energy release for the 1 gram of a atom, 1 gram substance, 1 gram of a uranium. Therefore, we have got the mass defect, then find out the energy. That is the energy release for the nuclear fission reaction. And the energy release in the nuclear fission reaction is find out by using the formula delta M into 931. Here delta M is equal to 0.2233 into 931. Therefore, the energy release is a 207.9 mega electron volt. But this energy is related. This energy is related for the 1 atom of a uranium. But here the 1 gram of a substance is given. So find out the number of atoms those are present in the 1 gram of a uranium. So when we find out the number of atoms those are present in the 1 gram of a uranium we can find out by using this formula, that is the Avogadro's number 0.6.023 into 10 to the power of 23. This number is known as the Avogadro's number into 1, that is a 1 gram substance is given, divided by the atomic mass number, and the atomic mass number for the uranium is a 235. So calculate this value and multiply by this that is a 207. We got the answer 5.33 into 10 to the power of 23 mega electron volt. So this is the amount of energy is released in the nuclear fission reaction. The next question is, the neutron separation energy is defined. The neutron separation energy is the neutron separation energy is defined to be the energy required the energy required to remove a neutron nucleus obtain the neutron separation energy of the nuclear Ca4120 and Al2713 from the following data. So when the neutron is separated from the nucleus, the reaction is that, or at that time also, a large amount of energy is released. Then kind of the energy released in the reaction when the neutron is released from that nucleus. So here the masses are given. The mass of a Ca, that is a when it is a released one neutron, 39.962591 AMU. Mass of a Ca41 is given 40.962278. Mass of a Al is given 25.986895 and mass of a Al27 is given 26.98151. So here there are two nucleus are given from which there are neutrons are separated. So here suppose the first reaction in which when the neutron is released from this reaction, the atomic mass number is becomes as a 40, and at the same time one neutron is released. And in the second reaction also, Al-27 when the neutron is liberated, its atomic mass number becomes as a 20 and one neutron is released. So find out what is the amount of energy is released from the neutron is released in the both the reaction. When the neutron is released from the nucleus, because we have got the mass defect and some amount of energy is released in this reaction. So first find out the mass defect, then find out the energy, and we have got the what is the amount of energy released in the both the reaction. So to find out this, there are mass are given, and when the mass different mass are given, add those values, and when we got the mass defect and find out the value of a energy release. So here the mass of a neutron is 1.008665. So here to find out the mass defect, the mass, all the values are given. Substitute all the given masses and find out the mass defect. When we substitute this value, that value is given as a 40. Mass of this Ca40 is given as a 39.9625 plus mass of a neutron. Mass of neutron is given 1.008665 minus mass of this Ca41, that is a 40.962878. Write down all the values because the mass defect is very small. So consider all the digits, and we have got the mass defect is 0.00878978, that is the AMU. So to find out the energy release, Q is equal to delta M into 931. Therefore, 0.008978 into 931, that is the answer is in the form of a mega electron volt, and the answer is 8.362 mega electron volt. So in this step, we calculate the energy release in this reaction. So from this nucleus, when the neutron is released, so there are two nucleus are there. So added the mass, two masses, and find out the mass defect, and then find out the energy release in this reaction. And the energy release in this reaction when the neutron is liberated from this reaction is a 8.362 mega electron volt. Then again find out the second reaction. In the second reaction, the reaction is given Al27. When the neutron is released, atomic mass number becomes as a 20 plus neutron. Then find out the mass defect. To find out the mass defect, the values are given. Substitute all the values. Mass of this Al20 is given as a 25.986895 plus mass of a neutron is 1.008665 minus mass of this Al27, that mass is 26.981541. So find out the answer, find out the mass defect, and that mass defect is find out 0.001338455454 AMU. Therefore, Q is equal to delta M into 931 mega electron volt. So substitute the value delta M 0.00138454 into 931. So the energy release is 12.89 mega electron volt. So here in this type of the mass defect of the energy release is depend upon the mass defect. So in this type we calculate or we can find out the energy released in the nuclear fission reaction as well as in the nuclear fusion reaction.